Look at using power series in order to estimate an integral. So here we have the integral from 0 to 0.35 of sine of x squared dx. And if you think about traditional integrating techniques, there's really no way to do this. So what we're going to do is we are going to use power series. So let's remember what the power series for sine is. Let's drop this in here. Okay, so here we have the power series for sine. Our integral over here, we need to do the sine of x squared. So the first thing we want to do is we want to create a power series for sine of x squared. So all we have to do is take the power series for sine, and wherever we see an x, we're going to put an x squared. So we have our summation notation. We can use that. And right here, I've got my x. So instead of x, I'm going to write x squared. And that's going to be to the 2k plus 1. Okay, and if we'll simplify this here. Let's go ahead and simplify this, and then we'll go look at this other expanded form. So now all I really need to do is simplify that exponent, negative 1 to the k over 2k plus 1 factorial. And then I can multiply these exponents, and I get x to the 4k plus 2, right? We multiply those exponents. You could also do the substitution in the expanded form. Wherever there's an x, you substitute an x squared. So this would be x squared to the third, which would be x to the sixth. And this would be x squared to the fifth, which would be x to the 10th. And you can double check and make sure that that's following this formula right here. So if we put 0 in for k, we'd get an exponent of 2. That matches. If we put 1 in for k, we'd get an exponent of 4 times 1 plus 2, which is 6. If we put 2 in for k, we'd get an exponent of 4 times 2 plus 2, which is 10. That's matching up. And we really didn't change this coefficient part, so that should be the same. All right, so now what we want to do is we want to go over here to our integral, and we want to replace the sine of x squared with its power series. And we could either do that in the summation notation, or we could do it with the expanded notation. And we are going to integrate that. So whichever you prefer, I think I'm going to go ahead and just do this in the summation notation. So this negative 1 to the k and this 2k plus 1, we're really going to treat these like constants when we're doing our integration. Here's my x term. That's what I'm integrating with respect to dx, right? So this is really just a constant times x to a power for a whole bunch of different terms. It's like it's a polynomial, right? This is just a polynomial. So, and in my polynomial, when I do the integral, I'm going to follow my integration rule, which is just going to, this constant will stay the same. I'm going to take this exponent and add 1 to it, divide by that, and then add 1 to this exponent up here. So let's go ahead and do that. All right, so I have the sum from k equals 0 to infinity of negative 1 to the k over 2k plus 1 factorial. And then the integral of that is going to be 1 over 4k plus 3 x to the 4k plus 3. All right, so now we're doing a definite integral. We're evaluating that from 0 to 0.35. So let's write it out like this. All right, so just like any other integral result, this is just a polynomial. Keep thinking of this as a polynomial. We're going to take our upper bound, and we're going to substitute that in for x, and then we're going to take our lower bound and substitute that in for x and subtract them. Okay, so we'll put 0.35 in for x. I think I'll write this coefficient with my k's together over here. Put my 4k plus 3 over here. Doesn't really matter. And then I'll have 0.35 to the 4k plus 3 minus. Now, I'm going to write all this out, but I'm hoping that what you can see is this second summation is just going to be 0. Again, I'll write it out for the sake of clarity here in the video, but if I was doing this work on my paper, I probably wouldn't even write this step out. Because if I take this sum right here, if I let k equals 0, I'm going to get some constant here, but this piece is always going to be 0. This piece right here is always going to be 0, no matter what k is. That's always going to be 0. So my first term when k is 0 is going to be some constant times 0. My second term when k is 1 is going to be a different constant times 0. 0 to the 7th, which is 0. When k is 2, I'm going to have some constant times 0 to the 11th, which is still 0. Right? So this part comes out to be 0. So what we're left with to evaluate our integral is this series right here. All right, so here is the summation that we came up with. Now remember, this summation that we came up with this by evaluating the integral. Oh, let's see if this is going to work here. The integral from 0 to 0.35 of sine of x squared dx. So this summation, whatever this value converges to, assuming it converges, is the value of the area under the curve of sine of x squared from 0 to 0.35. Now, does this converge? Well, let's take a look at what we've got. We've got an alternating series. So we need it to be decreasing, and we need the limit as k approaches infinity of this to be 0. Because of this piece right here, we're definitely going to have, as k approaches infinity, this is going to go to 0, and it is going to be decreasing as well. And you could do an alternating series test to see that this does converge and this area does exist. All right? Pretty easy to think about how this area would exist. This is always positive, right? So this x squared would be positive, right? And so 0.35 squared is going to be less than 0.35. 0.35 is the first quadrant angle, so we're all in the first quadrant here, and we should expect this to be a positive area. Okay, so how do we go about evaluating this to within, I think we were trying to get within 100th, right? Well, we could just do it term by term. So we could put 0 in here and work it out and see what we get. You could use technology to do this, but let's just go ahead and write it out. So -1 to the 0 power is 1. And then we'll have 0 in here will be 1 factorial, which is 1. And that's going to be times 3. And 0.35 to the 3rd. So let's work that out. So 1 divided by 3. 1 divided by 3 times 0.35 to the 3rd power is 0.14. Oops, I forgot a 0. 0.01429, and it looks like 6 repeating. All right, so this was when k equals 0. So let's do k equals 1 and add that on there and see what we get. So when k equals 1, it's actually going to be a negative up here, right? -1. And then I'll put a 1 in here. We'll have 3 factorial times 7, and then 0.35 to the 7th. All right, so I'm just going to pause the recording and punch this in and see what we get. Okay, so after I combine the first two terms, so this is the sum of just the first term. Okay, so the sum of the first two terms, so I took this and then subtracted that. I got 0.0142763,478. So these two answers already match. Gosh, what do we have here? They already match up to 4 decimal places. So we certainly don't have any error here. Probably just the first term, we're good to go. All right. So it only took one term, and we know that this is approximately 0.0142916, repeating approximately, right? Okay. So let's remember something else about this series. This is an alternating series. So if you remember the error in an alternating series, error in using an alternating series to approximate, alternating series. All right, let's say you add up the sum of the first n terms. How far off is that from the actual sum, right? Let's say this is the actual infinite sum, and you subtract those. And so you have the difference between the actual sum and the sum of the first n terms. This might be positive or negative, so we could look at an absolute value here to make it positive. This is going to be less than the n plus first term. That's a characteristic of an alternating series and the error in an alternating series. So if I look at this first term right here, if I look at the value of that when k is 1, which is the second term. So let's call this a sub 1. When k is 1, that's this term. So our a sub 0 came out to be this guy here, a sub 1, let's call it that, is negative 1 over 42 times 0.35 to the 7th. 1 over 42 times 0.35 to the 7th is 0.00. Let's see, I need 4 zeros and a 153. 1, 2, 3, 4. My calculator says 1.53 times 10 to the negative 5th. So my error in just the first sum, the sum of the first term, is going to be less than this, which is less than 100th already. Okay, so that's pretty dang accurate. Now, what the work that we've done, we can use that if we wanted to change the top bound. It really wouldn't matter. We can use all the work we've done. Let's say I want to do the sum from 0 to 3. It's going to take a few more terms to get this sum right. Well, we already figured out this summation right here. And remember how we got this summation with this 0.35 is we plugged in the upper bound. So let's go back here and let's say, what if I wasn't plugging in 0.35, right? What if I was just going to say b, right? Some random value of b. So this would be b, and then this would be b. All right, so we could find the integral from 0 to any value b of sine of x squared dx by looking at this alternating series right here. So this is the alternating series for this integral. So let's do that for 3, from 0 to 3. All right, so I just copied the summation over here, and I put a b here in red. Remember, this b is representing this upper bound right here. So I don't have to go through all the work again because it's the same function sine x squared. If it was sine x cubed, I'd have to go do a little different work. It wouldn't change it too much. It would change these, but okay. So now we're going to substitute in 3. Now this is where we might want to use some technology to see what's happening with our partial sums. We could also just look at the terms of this guy and find a term that is less than 1/100th. If we're trying to evaluate this integral within 100th, we could just start writing out the terms of this guy and find one that's less than 100th, and then it would be the sum of all the terms prior to that, which would get us our estimation within 100th. But let's go ahead and look at how we might use Desmos. I think I've got Desmos pulled up. Oh, here's the sine squared function, which is kind of interesting here. Maybe we'll turn this graph on later. Let's turn this off for right now. So I had the 0.35 in there, and I was doing the sum from 0 to 1. That was that decimal we got. Now I'm going to change this to, well, let's do 0 to 0. So that's just the first term when k is 0. So look at, we have 0.01429. Change it to 1. 0.01427. So I already had my first two decimal places. I could go 2 terms. Actually, that's 3 terms. Now that's 4 terms because I'm starting at 0. But you can see this is converging to this value pretty fast. And that is the value of the area under the curve, under this curve, from 0 to 0.35. Now wherever that is, right in here somewhere. Just this little area right here is equal to that value. All right, pretty cool. Now, if we want to do this for the integral from 0 to 3, this is kind of interesting, because now we're going to go 0 to 3. We're going to do all this area under the curve. So we're incorporating positive and negative areas. All we need to do is change this value, which was that b value. We're going to change that to a 3. And we can start looking at this summation and see what happens. So if I have 5 terms, I'm at negative 32. 6 terms is 12. It's really popping around here. So it's really fluctuating. 7, 8. Let's you know, we're going to have to bump it up. Let's bump up to 10. What we're looking for is for these first 2 digits to start stabilizing. So I got 0.79, 0.77. So I'm just changing this upper bound. Now I'm going to change the upper bound to 12. 0.77. Okay, so from 0 to 11 was 0.77. From 0 to 12, the area is 0.77. So I can say that the area is 0.77 to the nearest hundredth. If I wanted to go farther, I just look for that digit in the thousandth place to start stabilizing. It's a 3 right now. Let's see what happens if we change this. Now it's still a 3. So here we have 0.773 with 13 terms. Alrighty. So let's go over here and write this down. So we can say that this integral is approximately, oh, what is that moving around? 0.77. We could say I said within 100th, so we could say 0.77. It wasn't too hard to get it to 0.773 though, was it, with decimals? That's pretty neat. All right, pretty cool way to evaluate an integral using power series. Let's finish off by going back over here and looking at Desmos and looking at this power series one more time. So remember, this 3 was the upper bound, and we're adding up the first 14 terms here, and the output was the area under the curve, which is 0.77. Okay, now we're going to modify this a little bit, and instead of a 3 here, I'm going to put an x. Now this x right here is not this x, all right? This x is still representing the upper bound of the integral. So this x now is calculating the area under this blue curve from 0 to x by adding up the first 13 terms, or 14 terms, because we're starting at 0. I mean, we could get a little more refined if we go to 20 terms or 30 terms, but this graph is not gonna, we'll go 50 terms. There we go. It's not going to change too much the higher you get. Now let's analyze this. Let's see that this is making sense. All right, this is the graph of the areas. So let's look at this blue thing right here. So this blue graph, that's our sine of x squared. That's increasing. This is all positive area until we get to this point right here. X equals 1.772. Let's highlight that. X equals 1.772. Let's just make that like a dotted line. And okay, I won't get too particular. All right, so right here at this point, what happens to the area under the blue curve? It starts adding negative areas, right? So what happens to the total area from 0 to, say, anything past this green point here? The total area is going to start going down, right? Because we're adding negative area right here. Pretty cool. You see what's happening there? So right here at this point, when the original graph crosses from positive to negative, the graph of the integral is going to max out, right? It's going to max out and it's going to start coming down because we're adding negative area. And then what happens over here somewhere, right around 2.507, x equals 2.507. Let's make that green and dotted. That's another point there where here now I start adding on area. So now my total area is going to start to increase. And we see this relationship here. So hopefully you can look at that and sort of make sense that this summation, the sum of the first 51 terms of this thing, is actually giving you an approximation to the area under the curve of sine of x squared for different values of x, where x is the upper bound from 0 to x, right? This is representing the integral from 0 to x. All right, well, I hope that helps. I hope that picture helps solidify things for you. And this is just another cool thing that we can do with power series.